using PACE for land applications. So we have Fred Huemmrich from the University of Maryland, Baltimore County, and he's very interested in the hyperspectral remote sensing of vegetation. So he's going to talk to us about new hyperspectral-enabled land data products available from PACE and prospective terrestrial applications. So I'll bring up your talk here. Slowly. There it goes. Perfect. And take it away. Thank you.
Hi. First thing I want to do is thank Sky Kaplan, because without her work, none of this would be possible. So thank you, Sky. And the other thing I'm really excited about is that there's someone other than me here that's interested in land uses of PACE. So that's also an exciting moment in my life as we move forward, because we're going to take over in the end, because PACE is great and we can do lots of cool things with it. The reason I became involved with PACE from the beginning is I'm interested in ecosystem dynamics. And unlike all of the other kind of hyperspectral missions that are being proposed and are out there, we just get these little snapshots every so often of the land. But PACE gives us this repeated hyperspectral observations, and it lets us look at vegetation characteristics that we just have not been able to look at before. And one of the things that's really, really exciting about this is just these time series of hyperspectral data. Even on the ground, we hardly have those. You don't have them from aircraft. And so it's just seeing what they're telling us at the moment is just brand new. And so that's really exciting. So what I want to do is start by talking a little bit about what the land products are for those of you that aren't familiar with them. So the terrestrial surface reflectance data comes at two levels, level 2 and level 3. The level 2 data are swath data, and they are at the native spatial resolution of the instrument, which is 1.2 kilometers at nadir. But remember, PACE never looks at nadir. I always find it kind of an interesting thing that they tell you this, but what good is it? PACE always has a 20-degree tilt, and it has a fairly wide swath of like plus or minus 54 degrees. So there are angular effects that you need to take into account if you're working with this kind of data. The other data are level 3 data, and these are global data sets that have been gridded into lat-long grids. And they're either at 0.1 degree grids, which is about 11 kilometers to the equator, or at 2.5 minute grids, which are about 4 kilometers at the equator. And of course, that changes as you go north. The L3 data are available in daily, 8-day, and monthly averages. So you can choose the time period you want. At the present, the PACE surface reflectance gives you 52 selected spectral bands. I've just been informed that we're going to go to 5 nanometer full spectral bands. So I'm thrilled. This plot is showing the location of the spectral bands in a full spectra. PACE doesn't give us this full spectra beyond 890 nanometers, but you can see where it samples. And and again, like how much more information is available than these 7 MODIS bands that we presently had over land. The surface reflectance is calculated using L2Gen, and it matches up pretty well. This is a comparison between the PACE data and the PACE surface reflectance and the MODIS surface reflectance products for basically exactly the same place. And there's a pretty good agreement here. So we've got data that is matching up well with MODIS for continuation. So from this, you can generate these kinds of, so this is spectral reflectance of 2 sites, a tall grass prairie and a boreal forest. So tall grass prairie in Kansas and a boreal forest in Alaska. And really the thing that I really want to point out here is just look at all that variability. Look at all this information that's in this spectral data in the tall grass prairie, what you're seeing is it changing from being a bunch of dry grass into it greening up and being bright green and then going back to brown again. In the boreal forest, what you're seeing is the snow melting and then the system kind of greening up. Beyond this, but the problem is that often this spectral reflectance data, particularly when you're looking at these time series, are really kind of hard to wrap your head around. There's a lot of variables. And one way to deal with that is to calculate vegetation indices. So the PACE project has created a set of vegetation indices that basically can be an easy entree into using PACE data if you find the hyperspectral to be too intimidating. So there are 10 vegetation indices calculated by PACE. 6 of them are what we call heritage indices. These are all indices that can be or are calculated using like MODIS data. And these include NDVI and EVI. These are both generally related to how much green vegetation, bulk vegetation, are in a scene. There's NDWI and NDII. These are the normalized difference water and infrared indices. And these are really related to water content of foliage. Again, really kind of a bulk canopy water content measurement. The CCI, the chlorophyll carotenoid index, is related to the ratio of the chlorophyll and carotenoid pigments in the canopy. This is an index also that can be calculated with MODIS, but as we move forward in time, cannot be calculated with VIIRS. So, PACE is the only way to carry this one forward. And then the normalized difference snow index, it really is a measure of the presence of snow. And we've kind of included that because very often snow messes up these other indices, so it's good to know if you got it. But then, and what's really exciting to me is we have what we're calling hyperspectral enabled vegetation indices. So these are indices that we couldn't make with existing MODIS, Landsat, VIIRS instruments because they're using narrow spectral bands that just are not available from those instruments. And so one is the chlorophyll red edge index. It uses the red edge, the transition from visible into near infrared to detect chlorophyll. Carotenoid content index. Carotenoids are pigments that both provide photoprotection to plants, but also can enhance photosynthesis. There's the modified anthocyanin reflectance index, and anthocyanin content is also photoprotective, but also can show up in senescence. And then PRI, the photochemical reflectance index, and it's related to shifts in the xanthophyll cycle, which are plants use as stress responses, and so can be useful for determining photosynthetic light use efficiency. So we can look at these indices over time and see how they change. So this is the tall grass prairie again. And now we can see, so the blue line in that is the NDVI. And so this is typically what is used for studying phenology, looking at the greening up and senescence of the vegetation. But then we have the green line in there, which is the chlorophyll. And that chlorophyll index is really more related to the productivity of the ecosystem and sort of the potential productivity. And you see that it has a different timing of green up, a different timing of senescence. And then the third line in there that's kind of going the opposite direction is the ratio of the carotenoid index to the chlorophyll index. And since both of these indices are really related to the foliar content of that pigment and the leaf area, when you ratio them, you're basically removing the effects of leaf area and highlighting foliar change in chemistry. So we're able to see here, really for the first time, this seasonal change in foliar chemistry that goes along with the change in leaf area that that NDVI was giving us. Here's another example of for the boreal forest site. And once again, you see the NDVI curve. You see how largely different the chlorophyll index curve is. it is greening up much later than the NDVI is and dropping off earlier. And again, these are both, this is more related to the capacity of these systems for photosynthesis. But the thing that's really interesting to me here are these big peaks in the carotenoid chlorophyll ratios. And what that is indicative of is the photosynthetic, is basically the evergreen conifers turning on photosynthetically. So they're green all the time, but the pigment pools in them change as they convert from being in their winter state, where they're kind of asleep, to their summer state, where they're photosynthesizing. And we really can see that effect strongly in these curves. So we can look at these kind of dynamics, and that brings us to the pretty image that Jeremy already showed. And what we can do now is we can look at these pigments. In this case, blue are the carotenoid concentration, red is the anthocyanin, and green is chlorophyll. And we can see the whole globe change and the global leaf chemistry change with that. And in particular, as we run through a cycle here, look at North America, because it really shows up there. In the spring, it looks really blue, because, you know, and you see this yourself when you look at leaves. In the spring, when they first come out in the trees, they're kind of yellowy looking. They're not real green. That's because they're high in carotenoids, and the chlorophyll hasn't come into them yet. And then as they green up, we see the color here turn green, because chlorophyll comes in and fills them up. And then as we get to the fall, you see it suddenly start to turn red, and then we're seeing the senescence of the trees, and then we get in the autumn and the leaves turning colors. So we can see all of that in the dynamics of these systems. I love looking at this. It's kind of like a lava lamp, you know? So what does that get us, though, in terms of, you know, it's an applications group? What can we do with this to do something useful? So the hypothesis that we are really working with is that the factors that physiologically change in plants and plant canopies, including like leaf area, leaf angle distribution, leaf clumping, along with foliar changes in terms of pigment concentrations, these are all related to the physiological state of the canopy, and therefore also related to the productivity of the canopy. And so what we want to try to do is be able to use the spectral information to directly determine the primary productivity of the terrestrial ecosystems. And so the way we can do this is we can use data from eddy covariance techniques. So these are flux towers, like the picture here, in which CO2 flux is between the atmosphere and the ecosystem are measured, and we can use continuously, and we can use this to determine productivity. And so that gives us a really nice data set of ground data that we can compare with the PACE data. And conveniently, the NSF has funded an organization called NEON, the National Ecological Observatory Network, and their purpose is to observe the ecosystems of the United States. And to do this, what they've done is they divided the United States up into 20 different bioregions, and then within each of these bioregions, they have put in these flux towers to basically, monitor the ecosystems. So let me move fast here. So we can take that data. So what I've done here is I've taken 8-day average spectroreflectance data, matched it up for all of these sites, 47 sites, for every 8-day period that we had PACE data, so from March to October, and that gives me like over 1,000 points to work with. And the thing I want to mention is a year ago, I was at AGU doing a presentation about the same topic for the PACE thing to show what we could do with PACE. And I'd worked very hard to get like about 70 points out of DESIS data. So this is not only a quantitative, but really a qualitative difference in the ability to do this. And so ran a partially squares regression. And here we are with, these are ecosystems from tropical forests to Arctic tundra. And we can describe, 55% of the variance, is that 55? 65% of the variance with that alone. And you can see if you look at in the lower right plot, which is showing the coefficient weightings against wavelength, you can see how important the red edge bands are to determining this. And these were bands that just aren't in like MODIS data. You can improve this even more by actually, that was a single equation for everything. So, but if you go down to bioregion, you can improve this even more, bringing up we're now explaining 80% of the variance, and we've about half the root mean square error. But the other thing you see in this, if you look again at these coefficients in the plot on the left, that variability in the coefficients, we're really using information across the entire spectral range to really do a good job of describing the GPP across all of these different ecosystems. And then finally, we can just zoom down into one site. And so this is the Guanica tropical dry forest in Puerto Rico. And the orange curve here, this is against time. The orange curve is the GPP, is the gross primary productivity measured by the flux tower there. And the green line there is the NDVI. And you can see that the NDVI really just is not capturing the variability that we're seeing in this site. It starts out low, goes up, comes back down again, goes up. It's not doing it at all. But the blue line in there is what we derived from the PACE data, and showing how the PACE reflectance data can really pretty accurately track this variation in forest productivity that NDVI is just not capturing at all. So to wrap it up, we can really look at ecosystem productivity with PACE data. We can look at this across different vegetation types. We can zoom into specific vegetation types and really do a good job of it. And this reflectance-based approach is unlike, you could say, well, there's already a MODIS GPP product, but that MODIS GPP product depends on meteorological inputs. It needs to know like temperature and humidity, for example. This doesn't have any of that in it. Basically, the plants are telling us by their changes in their leaf chemistry that they're stressed and that they're changing their photosynthetic rates. So this is independent. So if we want to do things like look at future effects of climate change on a world that the ecosystem is going to be lagging climate change, this gives us a tool to do that. And I want to thank the National Ecological Observatory Network for freely providing all of that data. Thank you. Yeah, Petja.
Very quick question. So this is very exciting and so pioneering, so very cool. But what are your future directions, next steps? Tell us, where are we going?
Well, one of the things I want to do is biodiversity. So there's a whole question about what we can do, because we can do stuff with biodiversity here too, which is really interesting. But clearly we need, get more, I want to get flux data from regions outside of the United States and, to cover more of the world to get a better idea of what it can do. And then the other problem with the productivity is that I just blindly used those bioregions that Neon chose. But clearly, like ecophysiologically, that's probably not necessarily the best thing to do, and we probably can do a more efficient grouping that way. So that's, and then there is the problem of, then we have to use the hyperspectral data to do a better land cover classification to decide that. But all of these things can be done. The data are all here.
Excellent. And so it's a very large task to evaluate such products that you're producing. So maybe there should be a community out there working with terrestrial data looking at all of this and.
I am tired of being the only land person in Pace. I want a land community of Pace.
Me three.
And Sky does too, so there's two of us.
Three.
It's a revolution.
Okay, thank you.
Shall be called L. Like a place, or just L. Just
Oh,
Thanks, Fred. How far is the stretch to kind of take this even further into resource management? Like I'm thinking timber applications, wildland fire fuels.
So, the problem here is I think the biggest problem we have is that, like, the Pace data I'm using here is the 4-kilometer gridded data. So that is big for most land managers.
Okay.
So I think this has real value at another level, like for USAID looking for crop stress across Africa, things like that. But I'm not sure that it's really going to be useful to a specific farmer or a specific forester for the most part. But this gives us algorithms that we can develop and test at a large scale that can be applied to SPG and applied to these other satellites that we get the snapshots from, so we can put those snapshots in a context, and that'd be the other way to do this.
Fred, this is a great talk. It's really enlightening. Thank you. So, well, it looks like, with reflectance, you can really do such a good job. I don't think a MODIS GBP product is able to do such a good job. Meanwhile, you mentioned, you only use reflectance. This way, you do not really have to use meteorological data, soil properties, and so on, or maybe even vegetation type. This way, you can avoid many sources of uncertainty. So, theoretically speaking, you're able to estimate the GBP in a higher accuracy with much lower uncertainty. Do you think, this kind of GBP product can replace MODIS GBP and like products and be a global operational GBP data product?
Yes, I do. I think so. And frankly, we all know that the MODIS GBP product isn't really that good. I mean, and I don't want to diss it too much, but it was like the first try, and it really hasn't evolved much beyond that. And so there are definitely problems with it, and there are known problems with it, and hopefully this can get around that.
Thank you.
Yeah.
Hi, Fred. Beautiful presentation and graphics. Especially the difference between NDVI and productivity. I was wondering if you guys looked at links with evapotranspiration, or if...
No, that would be cool to, again, we've only started, I only was able to do this work starting in like the fall because I had to wait for the flux data to become available. So yes, there's tons of stuff to do. I don't have to do it all. Go out and do that.
Thank you.
Hey, Fred. I'm going to put you on the spot a bit. So, as you know, there's so many steps to getting here that can introduce various issues. Like there's sensor radiometric calibration. There's do I catch all the clouds? There's do I account for aerosols and surface, which can be spectral and directional effects. There's trace gas absorption, which can block out certain regions or cause biases. There's validation, which is not evenly distributed. Do you have a sense of which is like the tall pole where PACE team should focus most effort next?
Well, frankly, I think the tall pole is angular effects.
Okay.
We don't have a BRDF correction. And so we don't have a BRDF correction. And that is, and clearly when you start to look at these time series, particularly if you really want to make them even more dense than just the 8-day averages I was showing, you really have to take into account the angles. The angles will really affect this. And so I think, to me, that is like the big thing. Frankly, as you were well aware, the L2 gen doesn't have aerosols in it, which would be nice. But I'm surprised how well it works even without the aerosols.
Okay. Thank you.
Pleasantly surprised. Anything else? Well, thank you all.